Hello everyone and welcome back to a brand new video. Today I have for you the Gaussian integral using Feynman's technique or Feynman's integration method or differentiation under the integral sign. It goes by many names. Now I was incredibly excited when I came across this method of solving the infamously difficult Gaussian integral because I was previously under the assumption that there were very few ways to solve this integral. I know polar coordinates are the go-to method, I think, to solving this integral. However, what I have for you today is hopefully I hope it will become your favourite method of solving this integral because it's very satisfying, and I'll show you how it turns out. If you're unaware of what the Gaussian integral is, it's the integral of e to the negative x squared evaluated from negative infinity up to infinity, and it gives the result, as you can see here, of root pi. Now, there are only a select few integrals that give such nice values, such as this one. This is one of them. If you're unaware of what that function there, e to the negative x squared, is and or why I guess it's particularly difficult, it represents what's known as a bell curve, and this is it also goes by the name of the normal distribution, and it's used as far as I'm aware in statistics a lot of the time. That's definitely where I learnt about it. I'm sure it has many uses. It sort of crops up everywhere in the real world. If you were to distribute sort of a variable over a population, a normal distribution is what pops out. So if this was average heights of people, if this was heights of people, so you had, let's say, 4-foot people down here, and you had 7-foot people over here, well, the average is, of course, going to be 5'4". I'm only joking. The average is 5'8" or something like that. So yes, and so this crops up everywhere. And so we need to find the area underneath, and that is exactly what we are going to do. So to begin, what we do is, so we're first going to talk a bit about the actual function itself. So let's have a look. So we've got the integral from negative infinity up to infinity of e to the negative x squared dx. This is what we are working with. However, I hope you can realize that this, if I shade it in, this area right here, so if this is 0, well, infinity is going to be all the way over there, of course it is. This area from 0 to infinity is symmetrical and is equal to this area from 0 to infinity, and that would be negative infinity over there. So hopefully you can see that if we just consider this side of the function, then if we just double it, we will get the required area. We're allowed to do that. That's fairly standard. So what we can actually do is we can say that this is 2 lots of the integral from 0 to infinity of e to the negative x squared dx. And what we are going to do is we are going to give this a name. We are going to call this I, our integral. Okay, so now that we have that, let's go ahead and put this inside of a variable as well. Let's say that the integral that we want to find is 2 lots of some integral I don't know, we could call it IG for I Gaussian, or I'm going to call it I2. Okay, so I2 here represents the integral from 0 to infinity of e to the negative x squared dx. So if we can find what I2 is, then we can find what, let's call it I1 actually. We can find what I1 is because we just do 2 lots of that. And then we have our solution. Okay, so to start, what are we going to do? So we're going to, in classic Feynman technique, we are going to define a function, and we are going to call this function f of a. F of a, with a being our I guess you could call it the Feynman parameter. I don't know what the name of it is, but it's the parameter that we're going to be introducing. And what I'll do is I'll make that a different color so that it sort of stands out a bit more amongst all of the algebra that's about to occur. So this is equal to the integral from 0 to infinity. Now, what should our function be? Well, I'm going to show you the function, and hopefully I can make it make sense to you. What it's going to be is it's going to be e to the negative a squared times 1 plus x squared divided by 1 plus x squared. And you'll see why this is so powerful in a moment. Because when we take the derivative of this with respect to a, I'll show you what happens. So let's take the derivative of this whole expression here. So we're going to take the derivative with respect to a. I'd have to keep changing colour, so sorry it's a bit slow. So we're going to do the derivative with respect to a of f of a, and we're going to do the same on the right-hand side, of course. We're going to take the derivative with respect to a of the integral from 0 to infinity of e to the negative, change colour, a squared times 1 plus x squared over 1 plus x squared dx. Right, okay. Well, the derivative of f of a is, of course, just f dash of a, like so. Now, when we do the derivative, when we take the derivative of an integral like this, something a bit peculiar happens, and we have to do partial derivatives. And that's allowed in this case. So we're going to bring the derivative inside of the integral, and that's going to be the partial derivative with, that was an atrocious, there we go, with respect to a of e to the negative a squared 1 plus x squared over 1 plus x squared dx. Right. Okay, so you'll see what is about to happen. So we're taking the partial derivative of this function right here. So we're essentially taking the derivative with respect to a of that function. So that means that this is a constant. That means that this is a constant. That means that that is a constant, and of course that is a constant when it comes to a. So with respect to a, everything that isn't an a is just going to be a constant, of course. And so we can take the derivative of this, like so. So the integral from 0 to infinity of this function right here. So we're going to be taking the derivative of e to the negative a squared times 1 plus x squared, all divided by 1 plus x squared. Now, of course, in the a world that we are now differentiating in, 1 plus x squared down there is a constant, of course, with respect to a, and this 1 plus x squared up here is also a constant with respect to a. And so when we take the derivative of this, well, what are we going to get? Well, we are going to get the derivative of the function up top outside, sort of brought down. So that's going to be, what is that going to be? That's going to be minus 2a times 1 plus x squared, and then times e to the power of minus a squared 1 plus x squared dx, like so. And this is, of course, divided by 1 plus x squared. So hopefully you can see here that we are just going to be cancelling the 1 plus x squared and the 1 plus x squared, like so. And this gives us f dash of a is equal to the integral from 0 to infinity of minus 2a times e to the negative a squared 1 plus x squared dx. Okay, so we have differentiated inside of the integral, but don't forget the integral is with respect to x. We've got this dx right here. So now the a's are the constant. So let's simplify this. Let's bring something out to the front. So we've got f dash of a is equal to, now let me expand first, actually. So we've got the integral from 0 to infinity of minus 2, oh, I almost did a in a normal colour. That would have been absolutely life-ending. E to the minus, and then we're going to have a squared. I'm just going to write it, the squared in pink, because why not, times e to the negative a squared x squared, like this, dx. So all I've done there is distributed the minus a squared into that bracket there, and hopefully you can see how we have just got to this result. Now, as previously mentioned, anything that isn't an x is going to be a constant and can be brought out the front. So that's this right here. We're going to bring that out to the front. So we've got f dash of a is equal to minus 2a e to the negative a squared times the integral from 0 to infinity of e to the negative a squared x squared dx, like so. Cool, we have made progress. Now, what we are going to do is we are going to make a substitution to solve this integral right here. So, well, what substitution could we make? I've got an idea. Let's say let u equal ax. Now, I am just going to, for time's sake, write a as a black color for now. So setting u equal to ax, well, what happens? Well, when we take the derivative of this, so du, we're going to get, what we're going to get? Well, we're just going to get a, aren't we? Dx. We're going to get a dx, which means that dx, so this implies dx is du over a. Cool. What else? Let's look at the limits of this integral. So we've got the limit from the limits of 0 and infinity. So we've got the limit. So when x is equal to 0, well, what is u equal to? Well, u is a times x, so u is also going to be 0. When x is equal to infinity, well, u is also going to be infinity. Cool, so the bounds don't actually change. Let's go ahead and rewrite what we've got now, but with our substitution implemented. So this is going to be f dash of a is equal to minus 2, and then I'm going to just leave room for the a's, a squared, times the integral from 0 to infinity, because don't forget the limits stay the same, of e to the negative u squared du, and don't forget dx, so the thing we're replacing dx with is du over a, so that's over a, like so. Right. Oh, the a isn't pink. How dare I? There we go. Right, well, as previously mentioned, anything that isn't a u now in this case is a constant. This 1 over u that's sitting right here, 1 over a that's sitting right here can be brought out to the front, and it can be cancelled with this a right here. We're timesing the integral by a, and then we're dividing the integral by a. So that has the result of them two things just cancelling. So I'll use a different colour for this. Gone and gone. There we go. Let's simplify what we've got. So we've got f dash of a is equal to minus 2e to the negative a squared times the integral from 0 to infinity of e to the negative u squared du. Awesome, 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 awesome. Now, what did we say earlier? Let me scroll all the way back up. Here we go. We defined what this integral was. We've said that this is u2. Sorry, I can't speak today, honestly. I of 2, I sub 2. So we've got a name for this integral, from 0 to infinity of e to the negative x squared. We've called it I2. So let's go ahead and replace this integral, because that's exactly what we've got with I2. So we've got f dash of a, this is getting repetitive, is equal to minus 2e to the negative a squared times I of 2. Awesome, we are making excellent progress. Okay, what we're going to do now is we are going to integrate both sides now, because we have got the derivative of f. And if you remember from my previous Feynman technique video, once we get here and once we've got it in a form that we like, we're going to integrate it now. So let's see what happens when we integrate both sides. And the limits are going to be from 0 to infinity. So I'm just going to write that here. So we've got the integral now from 0 to infinity of both sides like this. Okay. So rewriting this, sorry, this is with respect to A. I should have said that, with respect to A. Now, if you recall, when we integrate, anything that is not in the A world in this case, so anything that isn't with respect to A, is classed as a constant. So what constants do we have? Well, we've got the -2 and we've got the I2, we've got that integral. So let's bring them out to the front because they are just constants. So we've got the integral from 0 to infinity of f dash of A, which we will evaluate in a moment, is equal to -2i2 times the integral from 0 to infinity of e to the negative a squared with respect to A. Well, I hope you can see this is I2. That is exactly what our integral is, I2. Because as you can see, and it's worth mentioning, it doesn't matter what the letter is. This can be an X, this can be an alpha, this can be a B or a C. No matter what X it is no matter what letter it is going to give some number. That's all it's going to give, because it's a bounded integral. It's going to give us just some number. So no matter what letter it is the same integral. And so what we can do is we can say that this is I of 2 again. Awesome, because what's going to happen? Well, we've got the integral from 0 to infinity of f dash of A is equal to -2 I of 2 times I of 2. So that is just -2 I of 2 squared. Now that's going to get confusing. So what I'll do is I'll put it in some brackets. There we go. I of 2 squared, like that. Right, okay, we're nearly there. We are very, very close to being there. We've just got this to deal with. Well, we know what this evaluates to, right? When we take the integral of a function, if we're taking the integral of a derivative, then we just get back the function that we started with. So this is going to be the limit as, let's choose a variable t approaches infinity of f of, let me actually just write it out like this first, f of A, like this. Sorry, what am I saying? Why did I choose t? That was stupid. No, it wasn't. T was correct. Of t and 0, like this. Okay, -2 I of 2 squared. So this is just solving an improper integral now. So this is equal to, this implies the limit as t approaches infinity of f of t minus f of 0 is equal to -2 I2 squared. Okay, well, I just had to move it because I ran out of room down there. Well, we can go ahead and evaluate what this is, as t approaches infinity. So as t approaches infinity, let's see what happens to f of t. What does that approach? Well, f of t, where was that? Well, that is, that's f of a, but with t substituted in. So that's like getting rid of this and substituting it in here. So what happens as t approaches infinity? Well, as t approaches infinity, this term right here, e to the negative t squared, that is going to approach 0. If that doesn't make too much sense to you, have a think. So as t gets bigger and bigger and bigger, why does this approach 0? Have a think about that. So anyway, so as t approaches infinity, f of t approaches 0. Awesome. Right, here we go. F of t approaches 0. Now let's see what happens when we substitute 0 into our f of a function. So f of a, you know what I'll do? I will copy it. I'll move it over for us. That would be a little bit easier, wouldn't it? It messes up the working on the left-hand side, but oh well. Right, so we're going to now substitute in 0, and let's see what happens. Okay, well, e to the power of negative 0 squared, well, that's just, of course, 1, isn't it? So we've got 1 to the power of 1 plus x squared, which is, of course, just 1. So f of 0 is equal to the integral from 0 to infinity of 1 over 1 plus x squared dx. Okay, so we've got a bit more to solve. Hopefully you recognize this integral here as being a standard integral, and the result that you get is arc tan of x, or tan to the minus 1 of x. So this is equal to the limit, and let's choose a different letter this time. Let's choose p, why not? So the limit as p approaches infinity of tan to the minus 1 of x, evaluated from 0 to p. Okay, so this is equal to the limit as p approaches infinity of tan to the minus 1 of p minus tan to the minus 1 of 0. Now, tan to the minus 1 of 0, that is 0. So that's gone. That's out of here. So we've just got this to deal with. So we've got the limit of, as p approaches infinity, of tan to the minus 1 of p. Okay, so what happens when p approaches infinity? Well, when p approaches infinity, this approaches pi over 2. This approaches pi over 2. So therefore, we know that f of 0 is equal to pi over 2, like so. Okay, I'm going to move that all out of the way now, just so we've got a bit of room. I'm just going to shuffle it all over there. Okay, so now that we know that f of 0, we can say approach as well, pi over 2. There we go. Okay, so we have got this right here. So we've got 0 minus pi over 2 is equal to minus 2 times I2 squared. So this is minus pi over 2 is equal to minus 2 I2 squared, of course. Let's divide by minus 2. We get pi over 4 is equal to I2 squared. Let's take the square root, and this implies that I of 2 is root pi over 2. Now we are so close. We have found what I of 2 is. Now, if you recall from earlier, if we know what I of 2 is, we know what the original integral is equal to. The original integral, I1, is equal to 2 lots of I of 2. So the original integral, I1, is 2 lots of I of 2. So I1 is equal to 2 times root pi over 2, which of course means that I1 is equal to root pi. Now let's just recall what was I1. I1 was the integral from negative infinity to infinity of e to the negative x squared dx, and this is equal to root pi. There we go. The Gaussian integral completely solved using the Feynman's method, or Feynman's technique.